Welcome, everyone. Thank you for joining us today. Before we start the webinar, I would like to say thank you for your continuous support and making hardwear.io Netherlands happen in a safe and welcoming environment this October. I'm glad to welcome today Davide, who has a degree in electronic engineering and is currently enrolled in a PhD program at STM Microelectronics in collaboration with the University of Montpellier. His research focuses on electromagnetic emission modeling in secure ICs. Today, Davide will share us with the result of the joint research with Philip, Thomas, and Alexander, and will answer the question how to perform electromagnetic side channel analysis by simulation. Now, just a little housekeeping before we get started. The presentation will last 30 minutes, followed by a 10-minute Q&A. Please share your questions in the chat and we'll answer them once the presentation is over. And we will also record the session and upload it later on our YouTube channel. Davide, now I would like to invite you to start your presentation. Thank you.
Hello, everybody. Thank you again, Andrea, for the invitation. Thank you for joining this webinar. Today, we'd like to talk about how to perform EM side channel analysis by simulation, because we all know that EM side channel attacks are a critical threat for security designers, because these attacks need only one leaky position, what we call an EM hotspot, over the C surface to totally break and compromise the security of a device. So it has become very, very hard and difficult to design circuit robust enough to resist the EM side channel attacks, especially because there is no CAD tool in the literature allowing to verify the robustness of ECS against EM side channel attacks. What we have at our disposal is power analysis tools. These tools allow to verify the robustness of ECS against power attacks, but they do not provide information about the electromagnetic field radiated by the EC, no information about the physical implementation or the power rail distribution. So the problem that often security designers have to face is that they have two products with the same netlist, but due to different synthesis or physical implementation, these products A and B have a totally different behavior and resist robustness against EM side channel attacks. So it is in this context that our researches took place. So today I would like to share with you 3 contributions. The first one is the development of a simulation flow able to emulate the magnetic field radiated by an entire EC. This is a flow based on a commercial airdrop tool that is RedHawk from the ANSYS company, on the use of the Biot-Savart law for everything that is the model of the electromagnetic phenomena that we observe on silicon. The second and I would say main contribution is a new methodology to correctly identify leakage EM hotspot prior to fabrication, so during the design stage. So methodology to correctly perform CPA attack by simulation, given the lack of noise in simulated traces. So we will differentiate in this presentation between leakage and EM hotspot. Leakage hotspot are the root causes of EM leakages, so the leaky CMOS gates that are at the origin of EM hotspot, and the EM hotspot are really the position where an attacker needs to place an EM probe to effectively capture a leakage in a design. And so then I will provide numerous comparison between simulated and experimental CPI maps. We will investigate the effects of EM probes that we use to collect EM radiation when performing EM side channel attacks. And we will show that we can use the flow to choose between different power and routing strategies, always prior to fabrication and during the design stage of a device. So I would like to start with the EM simulation flow. Then I will present the main problem that we have when we perform EM SCA analysis by simulation, given the absence of noise, the lack of noise in the simulated traces. And then I will propose a solution to this problem, a solution allowing to correctly identify EM hotspot during the simulation stage. And then I would like to validate both the methodology and the EM simulation flow by providing some practical examples. And I would like also to show why it could be useful to use this flow during the design stage of a component, of a device, to design secure EC against EM side channel attacks. So before talking about the EM simulation flow, I would like to do a quick recall about side channel attacks. When we perform these attacks, obviously we provide a clock waveform and the power supply to the crypto device. Then we charge a set of different messages, known messages, on the crypto processor integrated in the device, and then we can perform power or EM attacks. When we perform power attacks, we measure the global power consumption by inserting a little resistor between the power and ground pads of the device. If we perform EM attacks, we place a teeny EM probe over the C surface in order to capture the magnetic field radiated by DC. This is a magnetic field that is strongly dependent on the current flowing in the device, because we all know that a current flowing in a circuit generates a magnetic field in its neighborhood. And then the traces that could be power on EM traces are recorded and with a digital oscilloscope and then stored in a computer. And then we can look for a correlation between these traces and the data manipulated by the crypto device. And there are many type of analysis that we can do to look for this correlation. This is an example of a CPA attack. So based on the correlation coefficient, this simple example showing that we can identify the secret key among the other key hypotheses. So as I said, when we perform EM attacks, we capture obviously the magnetic field that strongly depend on the current flowing in the circuit. So the first step that we have to follow to model the magnetic field radiated by ECS is extract the current flowing in the AC. What we will do, we can make an hypothesis that is the following. We will model only the current flowing in the upper metal layers of ECS, because these are the hypotheses that these are the main contributor to the magnetic field captured by EM probes, because they are the closest to the EM probe when the CPA attack, the side channel attack, is performed front side. This is an hypothesis that we will verify during this presentation. So in order to extract the current traces of an EC, we can use a tool that is RedHawk from the ANSYS company. This tool is very powerful. It allows to get the temporal evolution of the current in each position of the EC, the current flow in the power and ground network of the EC. You can do that by placing virtual probes. You can see them here in yellow. Placing virtual probes on the layer you are interested in. In our case, we said this is the upper metal layers. In this way, we can build a big matrix containing a set of current carrying wires. This is an example of a wire that is simply the distance between two consecutive probes. And once we have this current matrix, we can model the magnetic field of the EC, starting from the magnetic field generated by each of these wires. So we'll use the Biot-Savart law. Actually, we manipulate a little bit this law in order to have the expression of the magnetic field as a function of all the coordinates X, Y, and Z of the space surrounding the wire. So in this way, we can get all the free components of the magnetic field, so the X, Z, and Y component. Here I reported the expression of the vertical component. Why? Because when we perform EM SCA attacks, normally we use horizontal probes, so probes that are parallel to the sea surface. These probes capture the vertical component of the magnetic field, but obviously you can use vertical probes. This will be the case later in the presentation. These probes, vertical probes, so capture the X or Y components. So similar computation can be done for the other components. And here I reported the vertical component for, depending on the wire, is vertical or horizontal from our point of view, so parallel to the X or Y axis. And once we have modeled the magnetic field, we have to model the magnetic flux, that is simply express the number of force lines that pass of the magnetic field that pass through the surface S of the probe. So it's simply an integral of the magnetic field over the surface S of the probe. And then we have to compute the electromotive force. This is simply the variation of the flux in time. We have to compute the electromotive force because when we have a variation of the magnetic flux in time, difference of potential is generated across the extremities of the probe. And this is exactly the signal that we record and visualize on the digital oscilloscope, sorry. And then the last step of our simulation flow will be the model of the probe. Normally, often in the side channel community, we use probe from the Langer company. These probes have different advantages, but have also a little inconvenient. This is a shielding effect. So as you can see here in the figure, probe from Langer company or other companies have a shape form that produce this shielding effect. So there is a part of the force lines of the magnetic field here in green that are correctly captured by the probe, but there is a part of the force lines that are not captured by the probe due to the form factor of the probe. So I didn't report the mathematical computation here because I just want to share the concept that we have to model, take into account this effect to improve the precision of our simulation. So now that we have the tools to model the electromagnetic phenomena that we observe on silicon, what we did at the beginning of my thesis of my PhD was to test this EM flow on a real test case. So what we did is to compare experimentally simulated CPA map on a test chip provided by ST Microelectronics, as I said, to test the effectiveness of the flow. But as you can see, the results, the maps are pretty different. So in particular, experimental maps show that reduce leaking areas. On the other hand, simulated CPA maps show that CPA can disclose the key almost everywhere over the sea surface. So in order to find the reason why we have these the differences, we needed to make a step back. So we analyzed once again a simple current carrying wire. So what I show you here is we can see three maps. The map here on the left is simply the correlation, so a CPA attack performed on a wire carrying a current E. So the wire is placed here on the center, and the CPA show that we have a strong correlation over the wire and null elsewhere. This is pretty coherent. Then we have the distribution of the magnetic field. The wire is always placed here in the center. This is the distribution in the space surrounding the wire. And then we performed a CPA attack on the magnetic field generated by the wire. What we expected was a distribution very similar to that of the magnetic field, but as you can see, is not the case because we have a strong correlation all around the wire. So this is a simple example that you can perform simulated CPA maps on the current traces, but you cannot do the same for the magnetic field because this approach is ineffective in identifying EM hotspot. Obviously, there is a reason behind this problem. The main reason are first of all that simulation are noise-free. Instead, obviously, experiments are not noise-free, are polluted by a noise that could be assumed as constant over the sea surface. And the second reason is that the correlation coefficient, that is the base that is involved in the CPA attack, is insensitive to the dynamic of variables. That means that by simulation, we can retrieve a leakage, even a position of the EC, where only few nano or femtoampere flow, which is obviously not the case in practice because where we have some picoampere in practice, we cannot exploit a leakage. So obviously we look for a solution for this problem in order to be able to perform this attack, EM attack by simulation. And the solution that we found that I would like to share with you today is the idea of computing the noise that has to be added to the simulated trace in order to hide a potential leakage. So to render the correlation, to destroy the correlation, to render the correlation insignificant. So you have here the expression of the noise that has to be added, the variance of this noise. This is an expression that that depends on the variance of the signal, the simulated signal. It depends on the simulated correlation, and then it depends on a variable that is called critical correlation. That is the value of the correlation above which the correlation must be considered as significant. So this is what we call the noise to add concept. And from this interesting, I would say, interesting expression, we can get another important expression, that is the minimal signal to noise ratio. This expression tells us which is the minimal signal to noise ratio that we have to observe by simulation if we want to exploit a potential leakage. So this is, in our opinion, a useful information for designers because they could be able to evaluate the dangerousness of a leakage prior to fabrication. And so in order to be able to modify the design and delete the leakage. So what we are going to do now is to apply this noise to add concept to the simple current carrying wire that we saw a few slides ago. As you can see, here we have the distribution of the magnetic field. We have the correlation on the magnetic field that leaks everywhere around. And here we have the distribution of the noise to add over the wire. As you can see, we have a really good agreement between the distribution of the magnetic field and the distribution of the noise to add. And then to conclude this part, we have to do one more step, because the method that I talked about until present is not enough to state that there is a leakage in a design, because the noise to add only tell us what is the level of significance of a correlation and what is the level of noise we have to add to destroy this correlation. But we all know that when we perform CPA-like attack, in order to exploit a leakage, we have to observe that the correlation of the correct key guess stand out from all other key hypotheses, so that the correlation of the correct key must be greater in modulus than the other key hypothesis. So the method, the criteria that I propose here today is to compute the noise to add only if the correlation of the correct key hypothesis is greater in modulus of than the other key hypothesis. Otherwise, in our map, or in our CPA map, we will put a 0. So at this point, we have all the tools to model the magnetic field of an entire EC. We saw how to correctly identify EM hotspot by simulation. So now I would like to validate both the simulation flow and the methodology, the noise to add methodology. So The goal is to, once again, to compare CPA maps, experimental simulated CPA map. The experimental CPA map have been performed by collecting EM traces with a Langer probe. And by simulation, we applied the noise to add concept on the electromotive force that we simulated starting from the current flow in the circuit, current extracted with RedHawk, the tool that we saw at the beginning. Current coming only from top metal layers, because we said these are the main contributor to the magnetic field. In this, we will verify this hypothesis. In this test case has been performed on a test chip provided by ST Microelectronics, test chip which integrates an unprotected IES. So in this first validation, what I would like to do is to validate, first of all, the fact that our simulation flow can take into account the effect of the probe geometry, so the probe diameter and the probe height. So what I did here is, let me say, a CPA knowing the correct key. So it's not a classical CPA with all the key hypotheses, is a CPA providing, knowing the current key guess, just to, as I said, validate the effect of the probe geometry. On the first row here, you have the experimental CPA maps. On the second row, you have the simulated noise to add maps. And what we did vary here is the probe height from 50 to 100 micrometers and the probe diameter from 100 and 150 micrometers. So first of all, we can observe that when you decrease the probe height, and when you increase the probe diameter, obviously the signal to noise ratio of the EM radiation captured by the probe is greater, the signal to noise ratio. So you have greater leaking areas with stronger intensities. And the second observation that we can do, the most important observation, is that our simulation flow seems to correctly reproduce these effects, because we have a very good agreement between each pair of experimental simulated maps. Sorry. Then, oh, okay. Then the second experiment that I would like to share with you is an experiment using vertical probes. We did that for two reasons. The first is obtaining another proof of the effectiveness of the flow, and the second reason was to validating that the hypothesis we did at the beginning, so about the upper metal layers. So in this case, in the first column here, the vertical probe is parallel to the upper rays. The rays are here in yellow. So in this case, the force lines of the magnetic field can easily be captured by the probe in this way. So we have a very strong correlation, a very strong noise to add here in the map. On the other hand, in this configuration, when the probe is is perpendicular to the upper metal layers, the force lines of the magnetic field cannot be captured by the probe. So the result is we have a very low correlation noise to add in our map. So this is very interesting, because it's a first confirmation that upper metal layers are the main contributor to the magnetic field captured by EM probes. And then it is another proof of the effectiveness of the flow, because as you can see, we have once again a good agreement between experimental and simulated maps. Sorry. So another experiment that we did is the comparison between front and backside analysis. So in this configuration, the probe is very close to the upper metal layers. On the other hand, when the chip is mounted in backside, the probe is very close to the lowest metal layers, usually the metal one. So what we thought at the beginning was that maybe the metal one in backside configuration could be the main contributor to the magnetic field, but it wasn't the case in practice, as you can see, because if you compare front side and back side, you can see that we have very similar leaking areas and very similar intensities. So once again, we can model only top metal layers when we perform EM channel attacks by simulation, because it is enough. Is enough. They are the main contributor to the field, to the magnetic field radiated. Once again, we can observe a good agreement between experimental and simulated maps, because we find that we have the same leaking areas with very similar intensities. So now, in this last part, last chapter of the presentation, I would like to show why it could be useful to use this flow during the design stage of a device, so prior to fabrication. We will use EM hotspot. As a reminder, leakage hotspot are the root causes of EM hotspot. So really the origin of EM hotspot in a design. To detect leakage hotspot, we will apply the criteria that we saw. So we will compute the noise to add only if the correlation of the correct key stands out from all other key hypotheses. And we will apply this criteria on the currents flowing, so not the electromotive force, but on the currents flowing the lowest metal layer, that normally is the metal 1. And to detect EM hotspot that are deposition of an AC, where we have to place an EM probe to effectively capture a leakage, we apply exactly the same criteria, but this time on the electromotive force simulated with our simulation flow. And when we look for EM hotspot, we can compare the result with the experiments. So by measure, we will perform a classical CPA on the EM radiations. So we will show in our map the the correlation of the correct key, only if the correlation stands out from other key hypotheses. So I would like to start from the identification of leakage hotspot, so the root causes of EM hotspot. And in this slide, I show you 4 time samples of the simulation. So what I did was to place about 100,000 of probes with RedHawk on the metal ones, on the lowest metal layer, in order to have a very good resolution. So what we can see here in time sample, between time sample number 1 and number 7, is the apparition of the leakage here in the highlighted area. This is an area encompassing the IOS in order to highlight the leakages. So we have here the apparition of the leakage. And then in time sample number 10, if between this time sample number 10 and 15, we have the spreading of the leakage along the power and ground grids due to the propagation of the current. So what we can see here in the highlighted areas here, really the wire segments that are close to some CMOS that are leaking. So I think this is it could be a very useful methodology for designer, because we are able to identify the leaking standard cell and then the leaking standard CMOS gate, sorry, prior to fabrication. So quick analyze a design, fix the eventual leakage, and then reapply the procedure in order to obtain ideally leakage-free design, even if obviously it's very hard, maybe impossible to have leakage-free design, but this is ideally the goal. And then we can apply the same procedure as said to identify EM hotspot. This time it will be on the electromagnetic traces, so the electromotive force by simulation. And the example that I propose is to compare 2 different ICS at design stages, so prior to fabrication. So in this case, we will compare 2 products A and B provided by ST to test chip that have a different power routing strategy. So in product A, we have the current flowing in the PDD rails, in the ground rails that flow in the same direction. And the product B have a little countermeasure so the current flowing in the VDD rail flows in opposite direction than the ground rail. So normally we should observe a little compensation of the magnetic field. So product B should be more resistant to EM SCA attacks. So here we can compare these configurations. So on column A you have the result for the product for the A product. In this column you have the result for the B product. So as expected, product B have a better resistance, robustness against EM SCA attacks because we have smaller leaking areas with lower intensities. And once again, another good news is that our flow can predict the robustness against EM attacks prior to fabrication, because we have, I would say, a good agreement between simulated and simulated experimental maps. So to conclude this presentation, I would like just to sum up a little bit the concept. We saw how to model the magnetic field of an entire EC, starting from the model of simple current carrying wire. We used the RedHawk, an airdrop tool from the ANSYS company, and the Biot-Savart law to model this magnetic field. Then we introduced the concept of noise to add that used to correctly interpret simulation result, because simulation are noise free, so we cannot perform classical CPA on the to identify EM hotspot prior to fabrication. Then we introduced we made also a link with the notion of signal to noise ratio. This is something more familiar to designers. And then concerning the achievements, we show that we are able to reproduce the entire magnetic field radiated by ECS by simulation, to localize both leakage EM hotspot during the design stage. We are able to modify, we could be able to modify the design and to reapply the same procedure to design leakage-free circuits. And then all this work constitutes, in our opinion, a first and complete solution to test the robustness of ECS against channel attacks prior to fabrication, so during the design stage of a device. So thank you for your attention. If you have any question, do not hesitate.
Thank you, Davide, very much for the presentation. I'm hoping that you all enjoyed it. Let's see if there are any questions. I would like to invite everyone to send the questions in the chat box so that we can read them out loud and answer them. And let's wait a little bit. Yeah, maybe it was a topic that has to be digested now first. All right, there is one. So Daniel is asking, is it planned to integrate this method in already existing tooling?
Actually, there is some work in the literature. That but there is a work that allowed to reproduce the EM field of ECS. There is another work that allowed to perform CPA attack by simulation, but this is as I said, the first work that provide CPA map, entire map of attacks by simulation. And yeah, the intention is to integrate this flow in our industrial process, but there is no really a existing tool that do something very similar. But yes, the goal is to render this work more even faster and precise, and to integrate it in our industrial process. I don't know if I answered the question, but
thank you. There is another question from Marco. He's asking, thank you for the presentation. Is there anything an RTL designer should learn from your modelization? Is avoiding upper metal layers really sufficient to avoid EM leakage?
but what we can learn is that the power analysis tool that are commonly used to test the robustness of ECS against such an attacks are not enough, because this fact that we cannot take into account the physical implementation of the device results in I mean, even if a design is free of any power leakage, we can identify EM leakages in the design. So what we can do, the one step that we can do is once you have here in the slide, where once you have identified the leaking standard cell, we can identify by performing RTL level simulation really the CMOS gates that are at the origin of the leakages. So work on these gates to delete the leakage. And the second question was, what is the second question? Is avoiding upper metal layers really sufficient to avoid EM leakages? But I don't know, because actually I didn't mean to say that we have to avoid upper metal layers. Just to say that the current flow in the normally in our test chip, the current flow in the upper metal layers is 40 times stronger than the current flow in the lowest metal layers. So if you just model these currents, it's enough to reproduce the magnetic field radiated by DC and captured by the probe. So it's largely sufficient and enough to correctly reproduce EM attacks by simulation.
All right, thank you. Do we have any other questions maybe? Yes, we do. Any idea on how the simulation time evolves with the complexity of the circuit to simulate linear, quadratic?
Actually, what I can say, because sometimes I don't know what I can say due to confidential problems, but we applied this flow also on how to say, more complex products. So because as I said in this presentation, I present only work on the test chip. I cannot say actually if it's linear or quadratic or something else, but I didn't notice a very increase on the simulation time. So even if the circuit is more complex, very complex, the simulation time is pretty the same. So I think this is something good for this work, because you don't need to multiply by 2 or 3 or 4 the simulation time if you analyze a more complex circuit. Thanks for the presentation. I don't need to let you show any picture of the test setup.
Yes, so I think you saw the last question. Did you show any pictures of the test setup used to capture the data? Curious what the probe looks like.
No, actually I didn't. Or maybe, yeah, at the beginning. Yeah, sorry. Yeah. So this is a classical Langer probe used to capture to perform such an attacks.
Maybe
So
if
these
you
are,
could zoom in a little bit.
sorry.
No problem. Great.
So yeah, this is an example of an horizontal probe. So it's parallel to the sea surface. So it captured the vertical magnetic field. And what maybe I didn't specify is that we have a motor that allow to displace the probe on the surface. So it allows to displace with a step that is some micron over the sea surface. So we have a very, very high resolution electromagnetic scan of the surface.
Thank you. Thank you answering all these questions. Do we have any more questions maybe? I think we answered all of them. Yes. So Davide, it was a pleasure having you with us today. Guys, don't forget to fill in the feedback form and share your experience with us. It would also be great if you'd give a shout out to Davide on social media. And thank you for attending. We hope you have learned and enjoyed this presentation and hope to see you soon. Bye-bye.
Thank you again for the invitation. Thank you. Thank you all. Thank you.